So this whole time we've been looking at series. I keep saying that the whole goal for us was to get to Taylor series, these series representations of functions. And now that we've built our way up to power series and convergence of power series, now we're ready to tackle this idea of a Taylor series. And first I just want to give the idea of what we're attempting to do with a Taylor series. And really it's a generalization of what you did in Calc 1 when you found a tangent line, or what we called a linearization of a function. So let's just remind ourselves of that and then talk about how we could extend that. So the idea was a linearization here was at a given point, right? You could have different linearizations depending on where you are on your function. So the first thing was to specify where you wanted to create that linearization. We often used A for that point. And then this tangent line, or linearization, had two key properties. It was supposed to intersect with our function at that point. So at A, the linearization and the function are equal. So first of all, L at A equals F at A, right? Next, the slope of that line should be the slope of the curve at that point. So the derivative of L at A should be the same as the derivative of F at A. So one way to think of a linearization is it's a new function, a linear function that matches the original function at that point and its derivative at that point. And from that, we can write the equation of what the linearization is, because we have a point. We know that it has to pass through this point on the function, which is the point A, f of A, right? That's the coordinates of that point. And the slope needs to be f prime at A. So using our point slope equation, L of x minus the y value of that point should equal the slope, m, times x minus A. And if we add that to the other side, we have our linearization formula from Calc 1. F at A plus f prime at A, x minus A. One thing to notice is this is kind of looking like a power series, right? Except for all we have is the first two terms, right? There's your zero term and your first degree term, right? Centered at A. Our coefficient seems to be involving derivatives of our function. So it's already hinting at a power series. So what was the point of a linearization? The point was it made a good approximation, or maybe an approximation. Let's not say good or not. But near A, it was supposed to approximate the function, right? So the point of a linearization is that L of x is approximately f of x, but only around here, right? The problem with the linearization is it's diverging away from the function, right? So only in some very small region. And depending on how fast the function is changing, that could be a very small region or a larger region. So in general, we would just say near A. So that was the point of making a linearization, was to use it as an approximation of the function, either because this function is transcendental and we don't know how to calculate it, or maybe this is a high order function and we're trying to do some quick computation. Linear stuff is very easy and fast to compute. A lot of linearizations are done in graphics processing, game development. A lot of the physics that has to be calculated so many times per second. that a linearization is used because the cost of computation is much lower, therefore increasing your speed. So there's many reasons why we might want to go with the linearization of the curve as opposed to the actual curve itself. Okay, so there's a natural next step here. If a linearization is good, wouldn't a quadratic be better, right? A quadratic curves, so we could maybe find a quadratic that kind of bends with that function instead of just being straight. But in order to do that, we would want to match another derivative, right? Because that thing has not only a first derivative, but a second derivative. So could we find a function, a quadratic approximation, so that it had the same value, same first derivative, and same second derivative? Well, if 2 derivatives is good, how about 3? How about a cubic that has the same value, same first derivative, same second derivative, same third derivative at a? And then what you're going to end up doing is adding higher and higher degree terms to this approximation. And then if you just let the number of terms go to infinity, you've got a power series. And that's really what Taylor's idea was to try and find a power series that would match the derivatives of some function you were interested in at some given point. So that is really the question that we're going to try and answer next is, could we find some power series, and I'm going to use s of x for the function notation. And the key is, what would those coefficients need to be, right? For example, here it seems like in a linearization, the coefficients are f and f prime. But what if we took this to infinite degree? What would the coefficients have to be so that we have this kind of a matchup, right? We want the thing to be the same as the function. So we'd like, when you plug in a to that power series, we'd like to equal the function at a, just like a linearization does. But when you plug a into the derivative of that series, we'd like it to match the derivative of the function, and then keep going. We'd like the second derivative to match, and the third derivative to match, and so on forever. And you can go forever, right? Because that's a power series. It's infinite degree, so you can take infinitely many derivatives. So that's our goal here with developing a power series is, could you find the right coefficients there so that you have a power series that matches some function? What is this function? It's some function that we typically can't deal with well, like a transcendental. Think of f as being sine, cosine, e to the x, natural log, tangent. So what we're going to try and do is make a power series that has very, very close match in behavior, really exact match at a, and then we'll look at how good an approximation it is, right? A linearization is only good in a very narrow area around a. Maybe we can go a lot farther out if we're matching all of these derivatives. So that'll be our goal. What are these? Next, we'll look at what do these coefficients have to be so that all of this stuff here is true. And it turns out there's a nice tidy formula, and once you have that formula, given any function, you'll be able to generate one of these series, which we're going to call a Taylor series. So we will look at that next.